Good morning. Today we'll continue reviewing for the final exam. We made some progress last time. I'll show you in a moment our page of all the topics with what we have done so far and what we're going to be doing today. As I said last time, I'm mostly trying to concentrate on everything before chapters 13 and 14 because we covered already those for our previous exam. So I'm going to be happy if we really review from 7 to 12. Okay. And I will put new information about that I have been given by the course coordinator finally for the final exam. So I'll make an announcement with all the details, but it will be available the same date as it was programmed in our original syllabus, whatever the date was, or in your schedule. That's when the exam will become available, and it's going to be a 48-hour exam. So I can confirm that now. It will be 48-hour. It will also be on not on our Canvas site, but on the Math 150B resources Canvas site. In the announcement, I'll also post a link. So make sure that you have accepted the invitation for that additional Canvas course. You were all invited earlier when we started doing online teaching. Everyone was added to that class, every 150B student. So make sure that you have accepted the invitation. If not, I'll link to it regardless, so that you can start checking. We still have this class and the next to be able to check. You guys can check that you have access. I also wanted to remind you about student evaluations. We're doing them online already, so please, I encourage you to do them and to write down any suggestions or constructive criticism that you may have, because we may still have to do online in the near future. Not so sure about the fall semester yet. So any type of suggestions that you may have for me to improve the learning experience would be much appreciated. So please do so if you haven't done student evaluations. All right, so let's see where we are. This is our list that we were working on of topics. And last time we did all the integration, so all of these topics are done. We did a little bit of sequences and partial sums, and the telescopic and geometric series. So this is where we are, and we'll continue working on these problems today. So sequences and series, remember, the best thing here is for you to be able to identify what would be the most appropriate test for an arbitrary sequence, right? So let's talk a little bit about that in general before we look at the problems. So series, convergence, and divergence of series. And what I'm referring to here is what are the types of tests that you can use and which ones are the ones that you should be, so that's the most important part in my opinion, be able to quickly identify what is the correct test that you should use, right? So which ones do we have? Let's make a list. We have the divergence test. This works only if what we have is not divergent. Otherwise, it's not really that useful. I mean, it only works if the limit is not zero, right? If the limit is zero, then it turns out to be inconclusive, and then you don't really gain anything from this test. So that's one. Then we have our basic one, so geometric series. Let me put them together. Geometric series and P series. So these are like our building blocks, which are quite useful for comparison and limit comparison. Then we have the ratio test and the root test. I'm going to group them together again because they sort of apply to the same type of problems. And then we have the integral test, which is a good test to try, but it's often difficult because you need to do an integral, right? So you should probably wait for that one till you have really no other choice. And then we have things like the alternating test and the absolute convergence test. And this is pretty much it, all right? So let's take a look at the problems, specifically those that are not really grouped into ones that you already know which ones should be, right? The problem here in our review sheet is that they're grouped by the corresponding sections. So sometimes that gives you a clue of to what is the type of series that you want to try, right? So let's see. Actually, I don't think they were. Let's see. We have all the way to F. Okay, so that actually is not that bad. So there's a bunch of them here. So let's try to see for these ones here, what would be the better test for us to try, right? So before we do anything, right? So we have a few of them here. Okay, so this one over here, let's start with A. So for A, let me mark it so we know which one we're working with. So this one over here, right? What would be the best series to use for this one? Well, let's see. So could we do the divergence test? Well, not really, because this obviously goes to zero, right? We're dividing one by something big, so it's gonna go to zero. It's not a geometric series, it's not a p-series. We could try comparison, but what would we compare to, right? That's a problem here for this one here. It's not clear what we would compare to because it's a little bit smaller than 1 over k. So we cannot use 1 over k because 1 over k is divergent, right? And this one is, you're dividing by something. This ln k makes it a little bit bigger in the denominator. So this is smaller than the series 1 over k. And 1 over k diverges. So we don't gain anything, right? For knowing that this is smaller than 1 over k. And we can't really tell that it's bigger than anything else. So this is one of those fews that the best one to do for this is actually the integral test. So the best thing for this one here, this one is actually the integral test. So here, integral test. Why? Because we have the ln k. What is the derivative of ln k? Is 1 over x. So that suggests that for this one, we should use the integral test. All right, now let's take a look at the next few. So what about this 1 over ln k? Well, this one, this time we can maybe do comparison, right? For this one, maybe we can do comparison. You actually can also do the integral test, but it will be a difficult integral. Because you don't have the 1 over k, you don't have the derivative of ln k here. So it will require integration by parts, not an easy integral to do. But here we can do comparison test because, you know, this one is the other way around. This one, ln k is always smaller than k. So 1 over ln k is bigger than 1 over k. So this one is bigger than 1 over k. So comparison test seems the way to go for this one. So comparison test would be the more appropriate one for that one. All right. Now let's take a look at the next. How about this one over here? Well, is it going to zero? Well, yes, because e to the something is bigger than k. So the number is definitely going to zero. Could we do the integral test? Well, yes, it will involve integration by parts. Could we do it in a different way? Yes, two possibilities here actually. See, because we have an exponent, we could do the ratio test. And we could also do comparison. So this one applies, has the two possibilities. We could do it with either comparison or ratio test, right? For comparison, you should compare it to something that is convergent. So maybe 1 over e to the k, or 1 over 2 to the k, you know, any geometric series that is smaller than this one. You just have to look for a 1 over a number that is smaller than e squared, which is actually very big. So here it could be ratio test. Ratio test would probably be the easiest. Ratio test, or could be also comparison test, could work as well. All right. So that's the most important thing, that you get an idea of which are the better ways to do it before you actually do it. Okay. So now let's try it out. Let's do a few of these. For example, let's do A and C. So let's start with A. So for A, we want to do the series of 1 over k ln k squared. All right. Switch to the camera. Okay, so to do this one, what we want to do is we want to do the integral, right? We want to do the corresponding integral. And so we want to do the integral from 2 to infinity of 1 over x ln x squared. And that is an improper integral, so that's how it ties it with the topic of improper integrals. So then this is the integral we want to do. We already have an inkling that the u substitution we wanted to do was ln x, because then du is 1 over x dx, and we do have the 1 over x dx there. So this integral becomes the integral of 1 over x dx, that's du, over u squared. And the new numbers for the u are from ln2 to ln b. All right? So now this is something we can integrate. It's like u to the -2. So that's awesome. We can integrate it. Let's do it. It would be, this is like u to the -2. So it's u to the -1 divided by -1. So it's -1 over u. And we're evaluating it from ln2 to ln b. So this is the limit when b goes to infinity. -1 over ln b plus 1 over ln2. And then when b goes to infinity, ln b grows a lot. And so this goes to 0. Michael asked at some point if 1 over k diverges from the p series. That's correct. And Nancy answered for that one, which is, that's correct, yes. So we got a number, so it converges. So that means the series converges. So this series converges. The integral test is good because if you get convergent here, then the series converges. If you get divergent, then the series diverges. It's a strong test. The problem is you need to do the integral, right? That's the downside of the integral test. Okay, so this one converges. We're done with that one. Let's take a look at some of the others. We have this part B. Okay, we can do all of them actually really quickly. So part B can be done super quick. That's the good thing. So I'll show it to you in just a moment. So for part B, 1 over ln k from 2 to infinity can be done quickly as follows. See, here's the thing. Like I said, see, we already know that ln k is smaller than k in general, right? At least for k bigger than 2, right? Bigger than e, actually, bigger than 3. So true for k bigger than 3. You don't even need to specify this because you know it that ln k is smaller than k. So if this happens, eventually this function will beat the other one, right? Maybe not right at the beginning, but eventually this will happen. And if this happens, then that means 1 over k is smaller than 1 over ln k. So this series 1 over ln k is bigger than 1 over k, and 1 over k diverges. So because 1 over k diverges, then this one diverges too. Correct? Why? Because it's bigger than a divergent one, right? So it's bigger than something that goes to infinity, therefore it should go to infinity as well. So that's direct comparison. You could also do a limit comparison, right? If you wanted to do limit comparison, then you would do the limit you would do the following limit. When k goes to infinity, 1 over ln k divided by 1 over k, that's k over ln k, which you could do L'Hopital's rule, or you could use the fact that we already know which function grows faster than the others. We know k goes faster than ln k, so this is infinity. And infinity works if you know the bottom one diverges. If the bottom one diverges, then by the limit comparison test, the top one diverges too. So since 1 over k diverges, then by limit comparison test, 1 over ln k diverges as well. Now be careful here, because if we had gotten 0, then you cannot conclude anything. That's when it's inconclusive, if the bottom one diverges. If the bottom one converges, then it's the other way around. If the bottom one converges and you get infinity, it's inconclusive. If the bottom one converges and you get 0, then you can conclude that the top one is convergent as well. Check it out again in your book if you don't know the special cases of the limit comparison test. All right, but that takes care of part B. And then for part C, what was part C? It was, I've forgotten already. Let me go back quickly. So I don't have the review sheet in paper with me, so I have to look at the screen. So it's k over e to the 2k. Okay, so this one we said we had choices. We could do comparison, or we could do the ratio test, right? And the ratio test is always appropriate when you have exponents. If you have exponents or factorials, then go for the ratio test. So let's do ratio test. Do the limit when k goes to infinity of is the k plus 1k divided by the kth term in absolute value. Here everything is positive, so we don't need the absolute value. So it's k plus 1 e to the 2 parentheses k plus 1 divided by k e to the k. When we make it only one fraction, this becomes k plus 1 e to the 2k, or 2k, my bad, divided by k e to the 2k plus 2. And that's the same as, let's see, k plus 1 over k times, and what is this? The 2k's go away, so it's 1 over e squared. And then when we do this limit, this goes to 1, right? Because it's a rational function, both grow the same rate, and the leading coefficient is 1. Or you could do L'Hopital's rule, or you could divide by the largest power in the denominator. Either way, this part is 1, so you get 1 over e squared, and e is like 2.7, so this number is definitely less than 1. So converges, so the series converges by the ratio test. Okay, here's a different way. If you want to do comparison or limit comparison, I could use a function 1 over e to the k. See, this one is a geometric series, right? It's like 1 over e, everything to the k. So converges by geometric test, geometric series test. Correct? Because this number is less than 1. So this one is convergent, and I claim that this one is bigger than that one. Claim this k over e to the 2k is in fact smaller than 1 over e to the k, at least for k big enough. And why do I know if this is true? So let me put a question mark for now. How do I know this is true? Well, if you cross multiply, what do you get? You get k. How is it? Is it true that k is smaller than e to the 2k over e to the k, which is e to the k? And of course, right, this is an exponential function. This is a polynomial. So this is true. So you can write it like this. True eventually, because k grows smaller than e to the k. Any exponential function beats any polynomial. So this one is bigger, and this one converges, means the other one converges. All right? Is that correct? Is that good? Any questions so far? Let's take a look at the others. The next page. So how about these ones here? Let's see. What do you think? Let's start with this. D. What do we think about D? Should be easy. Should be straightforward. The divergence test doesn't work because that clearly goes to 0, 1 over 1 plus root k. And what would be the best one for this to do? Well, comparison, right? Comparison or limit comparison to 1 over root k, which is a p-series, and we know it diverges because root k is to the power 1/2. So let me just put a little note here. This is easy. What we should do is limit comparison test to the series of 1 over k to the power 1/2. Right? That's the best, easiest way to do this one. Okay, how about the next? The next one, again, seems ripe for comparison, right? Comparison to what? Well, you look at the leading terms, right? This -1 and this +5 really don't factor into this. So this one is a little bit like k over k cubed. So the best thing to do for this one is to do the limit comparison test to the series that has 1 over k squared. Okay, and move it a little bit to here. And lastly, this one here, what do we do for this one? Well, this one has factorials, right? So it has factorials and powers. So for this one, what you should do is ratio test. And actually, in this particular case, we're lucky because for this one, we can also do the divergence test. How do I know that? Well, because we already know that this function k to the k beats k factorial in general, right? So we know that, let me see if I can do it. So in general, we know that this happens. So k to the k, so if you do k to the power k, that function is way bigger eventually than k factorial, right? It's one of our special ones in our book. So this one is bigger than k factorial, and because k to the k is bigger than k factorial, that means this limit will go to infinity. So then that means the limit of the quotient, so if you do the limit of k to the k over k factorial, that number will go to infinity. And of course, when k goes to infinity, all right? Is that clear? So by the divergence test, this limit is not zero, therefore this series diverges. I just did it with the divergence test. You can also do it with the ratio test. It's gonna work equally well, all right? So let's move it along. Let's move now to the ones. So this will happen again, by the way. These tests you need to also know when we go to power series. So when we go to power series, you use the ratio test to find out the interval of convergence, and you also use all the tests to figure out what happens at the endpoints. So this topic will recur on the next chapter, right? So we'll make an appearance on the next chapter as well. Okay, so let's move it along to the next. I'm gonna have to clear these drawings, and let's move it along to the next page, the next set of problems. So here are a few more series, and now the question is, these are all alternating, as you can tell, because we have this -1 to the k, and then the question is, are these converge absolutely, converge conditionally, or diverge, right? And the way to do any of these is you first need to do them with the absolute value bars, because if you do those and it's convergent, you're done. That's it. They're absolutely convergent. If the one with absolute value diverges, then you do the one that alternates, usually with the alternating series test. And if that one converges, then it's conditionally convergent. If that one diverges, then it's divergent. That's the procedure you should follow, all right? So let's pick a couple of these. Actually, these E and F are the same, right? I know, almost the same, it has a K on top, my bad. So let's do E, for example, or I don't know, C and E to pick one, or the one with secant maybe looks complicated. So let's do B and E. How about that? Let's do B and E. So let's start with B. So B is the sum from, should be K here, by the way. All of these are Ks. I don't know, there's typos here. It should not be n equals 1 to infinity. It should be K, okay? So from 1 to infinity, -1 to the K, secant of 1 over K. All right, let's take a look at this. Okay, so like I said, you first do the one with absolute value bars. And the absolute value bars, what it does, it gives this -1. And the secant, I don't know, right? Because it could be positive or it could be negative, right? We're not sure. But what we are sure is what this is approaching to, because when K goes to infinity, so in other words, let's try the divergence test. So now try divergence test. What is the limit of secant of 1 over K? Missing a letter here. Secant of 1 over K when K goes to infinity. Well, 1 over K will go to 0. So this will be secant of 0, absolute value of that. And secant is 1 over cosine, and cosine of 0 is, what is it?
1.
1. So this is 1. And because 1 is not the same as 0, this diverges. Okay, so it's not going to be absolutely convergent because the one with absolute value failed. So then we go to the one without absolute value. So for that one, we need to to check. So, so now try alternating test. So now we need to look at this one. And for the alternating test, we need two things. And we need that this becomes eventually smaller. And that's not going to work because this is approaching 1. And the other is that this approaches 0. So both of them are going to fail. The easiest one to check is that this does not approach 0, right? So the limit of secant of 1 over k when k goes to infinity, like we said, this is secant of 0, which is 1. And this is not 0, so it diverges. So this series, the original one, is divergent in general, right? So the original series is divergent. Okay, so let's now take a look at another one. Let's see another example. Okay, let's pick the other one. What about F? Let's take a look at F. So it's a series from 1 to infinity, negative 1 to the k over the square root of k cubed plus 1. Okay, so same as before, we first try the one with absolute value bars. Now everything here is positive except for the negative 1. So this becomes k over root of k cubed plus 1. And now this we're going to use limit comparison test to what? We're going to compare it to the one that is k on the top and k cubed without the plus 1 on the bottom. So it's k cubed with the square root is k to the 3/2. And when you simplify, this is 1 over k to the 1/2, which diverges by p series, right? So this one is divergent. So now we do the limit comparison test. So we need to do the limit when k goes to infinity of k over the square root of k cubed plus 1 divided by 1 over k to the 1/2. We simplify this, it'll become k to the 3/2 over the square root of k cubed plus 1. And if I rewrite this as with a square root, it will become square root of k cubed and the square root of k cubed plus 1. And I can now house that into one big square root of k cubed over k cubed plus 1. And this goes to 1 because the leading coefficients are both 1. So that's the square root of 1. And in the limit comparison test, if you get any number, including 1, so don't be confused, by the way, with the ratio test. For the ratio test, if you get 1, it's inconclusive. Here, if you get 1, you're happy. So this is a number, it's a number 1. So then these two behave the same way. So then by limit comparison test, the series behave the same way. So the one we have diverges. Okay, good. So now we need to try the one with alternating signs. Get more paper to see if that one converges, and for that we use the alternating series test. So then to do the regular one, we try the alternating series test. Okay, so we need to do this one, -1 to the k square root of k cubed plus 1, from 1 to infinity. So we need to check two things. First, the limit. Always start with the limit. Is this limit 0? Because if this limit is not 0, you're done. It diverges, right, by the divergence test. So what is this limit? Well, this limit is going to be 0 because we can write this as 1 big square root of k um, square over k cubed plus 1, right? So I put this k inside the square root as a k square. And now here, this limit, we can tell is 0 because the denominator has a bigger power, right? So this is now the square root of 0, which is 0. And that's the first condition we need to check. The next one is it true that this becomes smaller, right? So is it true that k plus 1 cubed plus 1 is smaller than k over k cubed plus 1. You can check the inequality, or you can use the derivative of this. And if the derivative is negative, then you're done. So I'm going to try to check the inequality. So is this true or not? So right now we don't know. So I have a question mark here. So how can I check it? Well, let's cross multiply it. So it will be k plus 1 times the square root of k cubed plus 1. Is that less than or not than k times k plus 1 cubed plus 1? I don't know, right? And how can I tell? Well, I want to get rid of the square root, so I'm going to square both sides. So now this will be k plus 1 squared times k cubed plus 1. That the square cubes the square root. And over here, k squared, k plus 1 cubed plus 1. And now I still can't tell, right? So I have to, I don't see any other way but to expand things out, right? I know it's not pretty, but that's the only way I see. So you would need to multiply these things out. So you would need to do k plus 1 squared, expand it, and you would need to do k plus 1 cubed, which I did already, and then you would need to still multiply this out and see what's going on, right? So let's see, this would be k to the 5th plus 2k to the 4th plus k cubed plus k squared plus 2k plus 1. And over here, k to the 5th, 3k to the 4th, 3k cubed, 2k squared. And now finally I get to cancel stuff. So this k to the 5th goes away. And then nothing else, right? Now let's see, what is it that we have? We have 3k to the 4th and k to the 4th, that's k to the 4th. 3k to the cube and k cubed, that's 2k cubed. 2k squared and k squared, that's k squared. And over here, 2k plus 1, right? And that's the thing now. Now, is it true that this guy beats that one? And this is obviously true because it's k to the 4th, right? Maybe it doesn't happen at the beginning, but eventually this number will be bigger than that. So this one is true because k to the 4th beats k. I don't even need these other ones, okay? Now, this is in general complicated sometimes, right? I mean, it's the final exam, so it's not enough to simply say, yes, this is smaller than that one. You need to justify it. Otherwise, points will be taken off, all right? I know that when we had it in class, maybe you just said, yeah, and this is smaller than that, so we're done. Here's another way. Another way you can do is with the derivative. So take a look at this function with x, change it to x, right, like that. And then check the derivative. If the derivative is negative, then you have what you want. That means the numbers are getting smaller and smaller. It's decreasing. So if f prime is less than 0, then f is decreasing, right? That's from calc 1. So we can try to figure out what's the derivative. Let's do it. So this is x over x cubed plus 1 to the power 1/2. So here's the derivative. The derivative is the derivative of the top, that's 1 times x cubed plus 1 to the 1/2 minus the derivative of minus x times the derivative of the bottom, which is 1/2 x cubed plus 1 to the negative 1/2 times 3x squared. All of that divided by the square of the bottom, which is x cubed plus 1, right? Now let's simplify this. This will be square root of x cubed plus 1 minus 3x cubed halves, the 3, the 2, the x's, and times x cubed plus 1 to the negative 1/2 divided by x cubed plus 1. All right, and now I need to know if this is positive or negative, right? And so I'm gonna multiply, I don't like this negative 1/2, so I'm gonna multiply by the square root of x cubed plus 1 top and bottom. So if I multiply by the square root of x cubed plus 1, this becomes just x cubed plus 1. And if I multiply by x cubed plus 1, this cancels. The square root of x cubed plus 1 is like x cubed plus 1 to the 1/2, so this cancels. And then in the bottom is x cubed plus 1 to the power 3/2. All right? Now, this is always positive, so I only need to know if the top is negative or positive. And the top is 1 minus 1/2 of x cubed. And now you can tell, right? I mean, this is obviously negative as long as x cubed is bigger than, and as long as this number is bigger than 1. So that happens really quickly. If you put 2, you get 8 over 2 is 4. Negative 4 is already beats the 1, right? So this is less than 0 if 1/2 x cubed is bigger than 1, i.e. x cubed bigger than 2, or x bigger than the cubic root of 2. And that obviously is true because we're gonna do it from 1, starting at 2, it's gonna work, right? So it doesn't work for 1. If you plug 1, then this would be positive, but after 1, it will be decreasing, and that's what we have. All right, so going back to the test, this works and that works, so those are my two conditions, these two. So therefore, it converges by the alternating test. And because it converges by alternating test, but the one with absolute value was divergent, this means this one is conditionally convergent. All right? So when the first one fails, but the second one works, it's conditionally convergent. When the first one works, the one with absolute values, then that's it, you're done. It's absolutely convergent. And if both of them are divergent, then it's divergent. Okay, questions so far? Okay, let's move it along. So that's the end of chapter 10, and that's, like I said, is sort of reviewed again when we get to the radius of convergence and the interval of convergence of these ones over here. So let's take a look at some of these from chapter 11. Now you can see that, so 11.1 is about Taylor polynomials or Taylor approximations, which is the same as, is very related to Taylor series. Taylor's polynomials is when you stop at a certain point. Taylor series is if you keep going, right? But oftentimes they ask you for the Taylor series, but they only ask to calculate the first 4 terms. Then you can, it's essentially like doing the Taylor polynomial of order 4. Okay, so we're gonna, I'm gonna skip these for when we get to Taylor series. Instead, I want to work on these ones right now. So radius of convergence. How do we find the radius of convergence? And it's easy. You always apply the ratio test. And then if you want the radius of convergence only, you can stop. If you want the interval of convergence, then you check the endpoints as well, all right? So let's do one where we do the interval of convergence. We can work on any of these. How about A and C. Let's start with A. So now we have a power series. The power series from 1 to infinity is x minus 2 to the power k. So it's centered at 2, 3 to the k, root k. And we need to find the interval of convergence. There's this one over here. A second. This one over here. And the question is, find the interval of convergence. So, like I said, ratio test. So we do the limit when k goes to infinity, ak plus 1 over ak, and it's going to look like this. X minus 2 to the power k plus 1 over 3 to the power k plus 1, square root of k plus 1. And then instead of dividing by the k1, I'm going to multiply by flipping it. Okay, so it's going to be now x minus 2 to the power k, 3 to the k, root k, like that. Okay, now here, this cancels with the k power here, 3 to the k with the k power here, and see what remains. So I have 1x minus 2, root k, 1, 3, don't forget this, right? We canceled the k, but there's another 3 here, 3 to the first power, and a root k plus 1. Okay, then I can take the things that are constant. See, the limit is with k, so everything that doesn't have k, I can take out of the limit, and that's what I'm going to do. I'm going to take this x minus 2 with the absolute value, the 3, and then all I need to do is this limit. Notice how I don't have the absolute value bars here anymore because this is positive. Now this limit is easy because this is a rational function inside the square root. The leading coefficients are 1, so this is like 1 over 1 at the square root of 1. So this is just x minus 2 over 3. Okay, now if this is less than 1, then it's convergent, greater than 1 divergent. So to find the radius of convergence happens when this is equal to 1. So when it's less than 1, convergent. And that means when x minus 2 is less than 3. So this is the radius of convergence, 3. All right? So the radius of convergence is 3. We are halfway there. We already know the radius of convergence. Now we just need to do the interval of convergence. Now to do the interval of convergence, let me make a little picture here. You could, I always like to do pictures. You don't need to, but it helps. So the center is 2. And we said that the radius of convergence is 3. So 2 plus 3 is 5. 2 minus 3 is negative 1. So these are the endpoints, 5 and negative 1. So we already know it's convergent in here. And we know it's divergent outside. And the only question is, what about the endpoints? Negative 1 and 5. And now that's the part we're going to check. And you check those one at a time individually, right? So if x is negative 1, what is this series? What is it? Well, negative 1 minus 2 becomes negative 3. And you can separate that negative 3 as negative 1 to the k, 3 to the k. And that's really good because these 3's go away, 3 to the k's. And the series that you get, now you can easily do, right? This one is convergent by alternating series test. How can I tell so quickly? Well, because it's kind of clear, right? What is the limit of 1 over root k? 0. And is it true that 1 over root k plus 1 is smaller than 1 over root k? Well, yes, because the square root of a bigger number is bigger than the square root of a smaller number. So These are easily checked, right? Here the inequality is so easy. We don't need to do any work. We can just say that it is true by just looking at it. So this one converges. We're done. What about if x is 1? Yeah, sorry, if x is 5, that's the other one, right? If x is 5, what's the other endpoint? Then when I plug 5 in here, what I get is 3 to the k over 3 to the k root k. This time there's no negative ones, so this is just 1 over root k. And that's the same like 1 over k to the 1/2. So I already know this one diverges by p series. So this one converges, this one diverges. So what is the interval of convergence? Is from -1, including -1, to 5, not including 5. All right? And that's the end of this problem over here. So they're all done in a similar way. So these are good because they let you review your series anyways. So all of these will involve the ratio test and then some other tests to check the endpoints. Okay, so I think we probably don't need to do another one. Otherwise, we're not going to have time to review everything else. So we can now take a look at this. So how can you find a power series for specific functions like this? And to do that, what you need to know are the known power series. So there's a few power series that you should know and you should have as reference. And I think they're all in the, let me check. I mean, we have a page in the book that has all of them. And it may even be in the back of the book as well. Let me briefly check. No, there's only the integrals, but the page you want to look at for this is, I'll tell you in a moment. Good. So we have the first one is the geometric one. You have to know that one, right? You need to use that one for reference all the time. So this one over here, like this one over here, the geometric series, all right? Then we have this one right here, which is almost like the geometric series, but is what happens when you substitute, instead of x, you substitute -x. So now it alternates, all right? So that's like a related one for the geometric series. Then after that one, we have the one for e to the x. You have to know that one. The one for sine x. It alternates and it goes over the odd factorials. The one for cosine, it alternates and goes over the even factorials. Okay. Then we have ln and inverse tangent. So you have to know that those ones as well. Right. So we have the one for ln x or ln of 1 minus x, either one of these two, which you can obtain by integrating the series 1, the geometric series, the 1 over 1 plus x. We have inverse tangent, so very useful also, and we do that by integrating 1 over 1 plus x squared. That's how we discovered it in the first place. Then don't pay attention to these ones, the hyperbolic sine and hyperbolic cosine. You can skip those. But at the very end of the page, we do have another one that we did as well, which is the one, the binomial series. You may remember this. So I haven't seen it too much in the final exam, but you never know. So just be aware of it. Okay, we don't have any problems in the final review sheet that use it, but it may or may not appear on the final exam. I have no clue. And so it's fair game, certainly. So let's take a look at the problems now. So here we need to discover some power series for the ones that you see over there. If we can figure them out. Some of them are kind of straightforward because you can just look at them from the page, right? They're right there in the page. Some others you need to figure them out on your own. So let's try, for instance, how we could do A, right? Just for practice. So how can we do the power series? Power series centered at 0. Doesn't say, but that's what they want. For f of x equals x over 1 plus x squared. Let's do part A. There we go. So how do we do it? Well, we need to start with one that we're familiar with. And in this case, it's the geometric one. So 1 over 1 minus y. I'm using y because I'm anticipating that we're going to substitute a value of y. So this one is just y to the k from 0 to infinity. So that's 1 plus y squared plus y cubed, etc. And this works between -1 and 1. That's the geometric series, right? And this kind of looks like this. And it would look exactly the same if I set y, well, without the bottom will look exactly the same if I substitute x squared for y, actually negative x squared, right? So set y to be negative x squared. And what happens? You get 1 over 1 minus negative x squared. That's going to be what we want, the bottom. And that's the same as negative x squared to the k, which is like -1 to the k, x to the 2k. Or in other words, is 1 minus x squared plus x to the 4th minus x to the 6th plus x to the 8th, etc. Right? So we're good now with 1 over 1 plus x squared. Now, how do we finish it off? Well, we need to now multiply by x to get the f. So f of x, the one we want, which is x over 1 plus x squared. All we need to do is we multiply by x, the one we found before. And let's multiply x times this. And just put it inside, so it will be -1 to the k, x to the 2k plus 1. In other words, that's the same as x minus x cubed plus x to the 5th minus x to the 7th plus x to the 9th, etc. Right? And in this problem, it doesn't say, but you can also calculate where does this work, right? So the first one worked for y's between -1 and 1. So the next one works when negative x squared is between -1 and 1. And this is always a negative number, so this inequality makes no sense. But this one over here is the same as 1 greater than x squared. So that means, again, x between -1 and 1. So this one. And then if you multiply by x, the same thing happens, the same bound. So this is good between -1 and 1, strictly. Those are the endpoints where this one works. Okay? So let's go back to the list of problems and see part B. You would also do it using the geometric one. So let's just do a few marks here before we finish it off for today. So for this one, you want to use the geometric, right? Use geometric. For the next one, you want to, of course, use cosine, right? Use the series for cosine. And then you're going to plug root x instead of x, right? That's the idea. And so these two are also self-explanatory. You want to use sine and ln. So I'm talking about these ones here. You want to use the power series for sine and then plug x squared and then multiply by x. And for the ln of 1 plus x is one of the ones we have in our list. And for the d over here, you want to use e to the y and plug x squared, then subtract 1, and then divide everything by x, right? That's how you could do part D. All right? So that's going to be it for today. So we still have tomorrow to review. If you have final questions, I know I haven't had too many of you asking questions here, but you can always tell me. I mean, if you rather do a different problem than the ones that I'm doing, or something that you have been struggling with, please ask. Your last chance will be tomorrow. And also don't forget to take a look at the announcement that I'll post on our Canvas site later today, so that you can know the information for the final exam. Let me just quickly tell you again. It will be 48 hours. It will be the same format as the 2 previous exams that we had. So it will be an assignment on Canvas. The difference is that it's not going to be in our Canvas page. It's going to be on the Math 150B resources page. But I'll link to it so you can find it. And 48 hours, I said. And yeah, that's it. So you need to, oh, another thing. It will be a bunch of assignments, actually. So because it needs to be graded by different people, it's better if every problem is an assignment. So make sure that you go over all the problems in the test. Don't miss any of them. And then for each problem, you need to upload a page, right? You won't be able to upload a single file with all the exam. You need to do it page by page, because your pages will be given to different professors to be graded, okay? So I'll let you know about that. Before we log off, any questions? You're welcome, guys. I'll see you tomorrow.